This video is going to go over Chapter 9, Section 2, preparing to test a claim about a population proportion. So in this lesson, we're checking the conditions for carrying out a significance test, which was the same conditions as we had from the previous unit. So those three conditions are that the sample is collected randomly, that the sample represents 10% of the population only when sampling without replacement from a finite population, and then also that it meets the large counts condition. And so what's changing here within large counts is instead of it being p hat, it's p naught. And so p naught is the proportion from the null hypothesis. So that's the value from our null hypothesis. And that still has to be at least 10, and you're still doing sample size times p naught and sample size times 1 minus p naught. And those have to be at least 10. So let's look at an example. So in the first one, we've got a reporter that claims that 90% of American adults cannot name the current vice president of the United States. To investigate this claim, the reporter selects a random sample of 50 American adults and finds that 28 are unable to name the current vice president. The reporter would like to know if the data provides convincing evidence that fewer than 90% of American adults are unable to name the current vice president. So what's happening here is that the null hypothesis is that the proportion, so P naught is 0.9, right? 90% of Americans cannot name the current vice president. The alternative hypothesis here is that P is really, P is really fewer than 0.9, right? So if I was conducting a hypothesis test, right, this is what I'm looking at. So I want to check, does this meet the conditions? So the first condition is randomness. Randomness is the easiest one to check because you're literally looking for the word random sample. Oh, perfect. There, we've collected a random sample. So D is not the correct answer because we have a random sample. The next one is the 10% condition. Remember, the 10% condition is only relevant when we're taking a sample without replacement, which would mean that we also are given a population size. So when we don't have a population size, if I think about 50% American adults, 50 is barely anybody in terms of how many adults there are in America. And so that means that that condition is met. So the 10% condition is good. So we've met the 10% condition, we've met the randomness condition. We want to check large counts. So to check large counts, we need to calculate n times p naught and n times 1 minus p naught. So remember, p naught is at 9.9. And then n is our sample size. So that means that n is 50. So we're going to calculate 50 times 0.9 and 50 times 1 minus 0.9. Okay, so if we do that, 50 times 0.9 is 45. That's at least 10. So we've met that requirement. And then finally, 50 times 1 minus 0.9. So 50 times 0.1 is 5. 5 is not greater than or equal to 10. So that means that we did not meet the condition of large count. So that means that our correct answer is no, the large count condition is not met. So if that last number was 10 or larger, our answer would have been A, that all three conditions were met. Let's look at another problem. A teacher claims that 55% of her statistics students have a strong understanding of inference for one proportion. To investigate this claim, she randomly selects 25 of her 50 statistics students and provides them with an inference problem about one proportion. Of the 25 selected students, 14 demonstrate a strong understanding of inference for one proportion. The teacher would like to know if the data provide convincing evidence for more than 55% of her students have a strong understanding of the topic. Have the conditions for inference been met? So her claim, right, her null hypothesis is that P is equal to 0.55. The alternative hypothesis is that it's actually more than 55%. So P is greater than 0.55, right? So if we were testing this claim, that would be our null and alternative hypotheses. We want to check the three conditions. So let's check randomness first. So remember, randomness, we're literally just looking for a random sample. So, or collected a sample randomly. So she randomly selects, that tells us that her sample was random. So that is not the reason that we might not be able to meet the conditions. Okay, so that condition's met. Next condition is the 10% condition. Okay, so if we're talking about this, she has 25 of her 50 statistics students. So the population is her statistics students, right? So this is our population. Whereas in the previous problem, our population was American adults, right? So looking at that population, we don't have a number here because there are an uncountable number, right? It's a large number. So 50 was a drop in the bucket. That was barely any percentage. If my population is 50, she says she has 50 statistics students. So that means that her population is only 50 and her sample is 25. We think about what percentage that is, that's half. So this condition, we're doing 25 divided by 50, and that's 0.5. And that's supposed to be less than 0.10, right? And that is not true, right? So 50% is not less than 10%. So the correct answer here is that the 10% condition is not met. Okay, so only when they give us population size will this potentially be the condition that is not met. From here, we're going to move on into a calculation. So the rest of this is calculating a p-value and then using that p-value to either reject or fail to reject the null hypothesis. So in this first example, we have, according to historical data, it is believed that 12% of American adults work more than one job. Okay, so they're telling us the null hypothesis is that P is equal to 0.12. To investigate this claim is still accurate, a random sample of 100 American adults is selected. So that's our sample size is 100. Think about your 10% condition, right? So random was met. And then we've got 100 is not very many American adults in the grand scheme of things. It is discovered that 18 of them work more than one job. So our p hat is going to be 18 divided by that 100. Which means that p hat is going to be 0.18. Okay. So remember that this one, if we're looking at our formula, this is p naught. It's the one from our null hypothesis. A researcher would like to know if the data provide convincing evidence that the true proportion of American adults who work more than one job differs from 12%. So our alternative hypothesis is that P is not 0.12, okay? And so remember that this is two-sided. And so that means that P could be less than 0.12 or P could be greater than 0.12, that we aren't qualifying as to what value that is, just that it's different. So looking at our sample, it's bigger, right? but we still have to test the probability that it's all bigger or smaller, okay? So since it's two-sided, this one's going to be a little bit more complicated than some of the other ones. So we'll talk about what those would look like in the example when we get to that point. So they give you a link to the z-table because we're going to need that for the p-value. So the z-table is going to help us find the p-value. The formula gives us the test statistic. So the test statistic is that z-score. Okay, so let's start with finding the z-score. So we've got p hat is 0.18, we've got p naught is 0.12, and then we have the sample size of 100. So I'm going to plug all that in. I'm just going to set up my structure here so that I can values. Okay, so p naught, or sorry, p hat is 0.18. So we're doing 0.18 minus p naught. I'm going to do p naught in green. Minus 0.12 over the square root of 0.12 times 1 minus 0.12, all divided by my sample size of 100. Okay. So if I calculate this, the numerator is 0.06. And the denominator, so if I take the square root of that fraction, I get about 0.0, whoops. .325. And then dividing that, I get about 1.85. So that's my test statistic. So I'm going to kind of populate my answer here. So z is equal to 1.85 is the first part of my answer. The other part is going to be the p-value. So what I'm looking at then is I want to find the probability that z is not equal to 1.85. And my not equal to, so that inequality comes from this here, differs, right? So when it says differs, I'm using not equal to. So what this means is that I want to know what is the probability that z is greater than 1.85 or that p is or the probability that z is less than 1.85. So what this means is that I'm going to have to add two p-values together to find this because it's asking if it differs, right? So if it's an or, I'm adding. So I need to find the probability that z is greater than 1.85. And I need to find the probability that z is less than negative 1.85. Okay. So when I'm thinking about this here, I'm looking at this area and this area. The good news is that those two values are actually the same, okay? So remember that because this is greater than for the first one, I'm either doing 1 minus the p-value there, or I'm doing the p-value at the opposite, okay? So I'll show you the long way, right? So since z is greater than 1.85, that means that I'm going to do 1 minus the number here on the z table. So if I look up positive 1.85 on the z table, so 1.8 and then 5 is 0.9678. So 1 minus 0.9678. So again, because this was greater than, that's why I'm doing the 1 minus part. I could also look up negative. So we'll see that that number ends up being the same. So when it's less than, I'm just looking at that number. So negative 1.85, 1.85 is 0.32, whoops, I forgot a zero, 0.0322. So notice that if you subtract 1 minus 0.9678, that's actually also 0.0322. So my value is 0.0322 plus 0.0322, which means that the p-value is 0.0644. So remember that the only reason that I had to calculate both of those probabilities is because I used not equal into my alternative hypothesis. So because it said differs. If it said less than or greater than, I would have only found one of those values and that would have been the answer. So it would have been 0.322 if it had said less than or greater than. So from this, we're going to then decide using the alpha equals 0.05 significance level. So remember that we're comparing our number to alpha. So 0, our p-value is 0.0644. So we want to know, is that greater than or less than alpha? So if alpha is 0.05, because that's what they're telling us here, right? They can change that number. That comparison is that this number is greater. So notice that this tells you in all of them, the p-value is greater, is greater, is greater. And so we need to know which one's correct. So if the p-value is greater than alpha, that means that we're going to fail to reject, okay? So we're going to fail to reject always the null hypothesis. So the correct answer here is C. So ultimately you have this thing. So your p-value is greater than alpha. You're going to fail to reject HO. Because it's always either rejecting or failing to reject the null hypothesis. If your p-value is less than alpha, then you're going to reject your null hypothesis. So you should automatically be able to eliminate anything that has alternative hypothesis. You don't reject the alternative hypothesis. So the only two possible answers were A and C, just knowing that we always work with the null hypothesis, not the alternative. So that is the lesson for 9.2. And that covers all of the different types of problems that you will see in the quiz.